potassium pump, right? Although we haven't been speaking about that, we talked about it initially. We want to still remember that it's on the basolateral surface of the cell. It's turning, sodium's out, potassium's in, and it's creating the gradients that allows for the movement of these ions through the channels that we have been speaking about, okay? So sodium potassium pump is here. It's creating the gradient, right? We said that 20% of the negative environment in the cell is directly owed to this pump because more positive charge is leaving the cell, less positive charge is coming back in. And then 80% is indirectly owed to the pump because the pump is creating the gradient for these ions to then move passively through their channels, okay? So we still want to remember the sodium potassium pump is a really important part of this resting membrane potential. All right. Now the resting membrane potential is actually closer to the equilibrium potential for potassium. That is going to be crucial in us speaking about the action potential later on. So the resting membrane potential is -70 millivolts, meaning that there's negative charge, an excess of negative charge inside the cell. The equilibrium potential for, for potassium is -94 millivolts. And that means that the inside of the cell has an excess of -94 charge when compared to the outside of the cell. And as you can see, the resting membrane potential is much closer to the equilibrium potential for potassium. And the reason for that is because the membrane is more permeable to potassium, okay? So because the membrane is more permeable to potassium, when the cell is at rest, its membrane potential is going to look a lot more like potassium's equilibrium potential than it will look like sodium's equilibrium potential. Sodium's equilibrium potential is really positive, so it's really far away from the cell's resting membrane potential. And that is really a reflection of the decreased permeability of the membrane to sodium, as well as the strong inward driving force that we saw. Because sodium has chemical driving force moving inward, electrical driving force moving inward, it's got a really strong inward driving force. And therefore it has a really positive membrane potential, a positive equilibrium potential, and it's going to be really far away from what the cell looks like at rest, okay? So just going on to further clarify that here, if the membrane potential is not at equilibrium for an ion, the electrochemical force is not zero, right? Remember, if the membrane potential is -70, it's neither at -94, nor is it at +60. And so we're going to see the movement of both of these ions. Only when the membrane potential is the equilibrium potential of a specific ion will that ion be at rest. If the membrane potential is not the equilibrium potential of that ion, we will continue to see movement that will attempt to approach the equilibrium potential of that ion, okay? And again, I'll kind of clarify this as we go here. So the net force that is acting to move the ion across the membrane is going to act in a direction that favors that ion approaching its equilibrium. In other words, potassium's equilibrium potential is -94. That means when potassium moves, it's going to be moving out of the cell, and it's going to be, that means at rest, when the cell's at rest at -70, potassium is going to be moving out of the cell so that we could approach that -94. It's going to be trying to move to get to its equilibrium potential. The same thing is true for sodium. Sodium has an equilibrium potential of +60. And so when the cell is at rest at -70, the movement of sodium is going to be favoring that inward movement, right? It's going to try to be making the cell become more positive so that it could approach potassium's equilibrium potential, which is +60. Okay, so the movement of our ions when the cell is not at rest, let me rephrase that. The movement of our ions when the cell is, when the ions are not at equilibrium, right, when the cell is at rest at that -70, is going to be in an attempt for these ions to approach their equilibrium potential, okay? And the strength of the net force is going to increase the further away we are from the ion's equilibrium potential. So just jumping back here to kind of explain that further, Just jumping back here to try to explain that further here, when the cell is at rest, right? This is kind of the condition that we're thinking about. It's at negative 70 millivolts, and so it's neither at potassium's equilibrium potential of negative 94, nor is it at the positive 60 millivolts, which is sodium's equilibrium potential, okay? What that means is that when the cell is at rest, both of these ions are going to be moving to try to approach their equilibrium potential. Because negative 70 is very close to negative 94, potassium is going to be moving out of the cell, right? Trying to approach its equilibrium potential, which means that positive charge has to be leaving the cell for us to get to that negative 94, but it's not going to be doing so in a strong way because this is very close, right? Negative 94 is very close to negative 70. And so there's going to be a weak outward force for potassium as it tries to approach its equilibrium potential from that negative 70. On the other hand, sodium has an equilibrium potential of positive 60, which is really positive, and it's also really far away from the resting membrane potential. So when the cell is at rest, sodium is going to want to move in an attempt to approach that positive 60. So it's going to be moving into the cell. Remember, it's a positively charged ion, and so moving more of that into the cell makes up this positively charged membrane potential here, positive 60. And it's also going to be doing so in a very thrustful, very strong way because it's very far away. It's more of a force, more of a gradient, more of a driving force, right? For it to move into the cell as it tries to get to its positive 60 equilibrium potential. All right. I hope that makes sense. So the strength of the net force increases the further away the membrane potential is from the equilibrium potential for that ion. All right. So when we have a resting cell at negative 70 millivolts, right, and bearing in mind that potassium has an equilibrium potential of negative 94, the membrane potential is 24 millivolts less negative than the equilibrium potential for potassium. So the electrical force into the cell is going to be lower. The chemical force out of the cell is going to be higher. And then the net force, the net general direction, or the ECDF, is going to be outward, but it's also going to be weak, right? Because we subtract that weaker force from the stronger force. And then the membrane is going to be highly permeable to potassium as well. That's another thing that we want to bear in mind. So we have a net weak force because we have an outward flow, but we have more of a permeability to do so. Taking sodium, on the other hand, when the cell is at rest, again, we want to think about that negative 70 millivolts. That's the state of the cell at rest. Sodium is going to be moving in an attempt to approach its equilibrium potential, which is positive 60 millivolts. And so if you look at the difference, right, how far away is the cell, how far away is the cell's membrane potential from the equilibrium potential of sodium? It's going to be 130 millivolts less negative than sodium's equilibrium potential, right, that negative 70. And so the electrical force is going to be into the cell. The chemical force will also be into the cell. And so again, we simply combine those two forces and we're going to have a strong inward thrust for sodium to move into the cell, but it's going to have less opportunities to do so, less channels, right? Which reflects that lower permeability to sodium. Okay. All right, and then just putting all that together, we have a small sodium leak at rest because of its high force and low permeability. We have a small potassium leak at rest because of its low force but high permeability, right? So again, the balancing out of those two movements of those two ions, and that in coordination with the sodium-potassium pump is what establishes that negative 70 resting environment.